Thanks for the warm introduction. My name is Marcello, dividing by zero at Herodotus. Some people say I'm similar to this goblin. And yeah, today I would like to talk about storage proofs. I hope I will do my best in this short time frame of 20 minutes. Okay, cool. So first off, I would like to establish some very basic context. So first off, maybe let's talk about different applications of like ZK in quotes, because it's a pretty broad term. So I really like to define that it's mostly split between validity proofs and like privacy. And most of the well-known applications for validity is, of course, rollups, and for privacy mixers. And I would like to emphasize that storage proofs fit more into the validity category. So to establish some more context, let's talk about a mental model you should apply when listening to this presentation and thinking about validity proofs. So basically, you can take some logic that can be represented with like some ZKVM through a circuit, and you perform a bunch of constraints there. And this is this function basically. And then we have two types of inputs to this function. It's very important for those of you who are technical. These things are basically stateless, so there is like no state in that. So it's about like a bunch of inputs and assertions inside. So again, there are two types of inputs, public and private ones. As the name can suggest, public inputs are visible by both parties of the protocol. So in this case, the prover and the verifier, whereas the private inputs are seen only by the prover. So maybe to give you some more context on how this can be applied, and also important disclaimer, 99% of the cases, the verifier is a smart contract living on-chain. And this is a very important constraint. And that said, normally we should minimize the amount of public inputs, especially when it comes to dealing with storage proofs, whereas private inputs, we can be maybe less constrained on that side. So just to finalize this part, private inputs are seen by the prover, whereas public inputs are seen by both the prover and the verifier. Example, a Merkle root is usually a public input, and a private input is, for example, inclusion proofs. Cool. So now that we have some basic context, let's get to the actual topic of the presentation. So what are storage proofs and how we define storage proofs? So for us, storage proofs are a set of cryptographic proofs or a single proof that can attest to the validity of some information stored in a broader data set that is cryptographically committed. And such data set can be, for example, a blockchain, a rollup, and an L1, a state tree, whatever. And also, very important disclaimer, it's part of the, we also prove the execution of a workflow that makes this possible. So now, why would you care about storage proofs, especially today? So maybe I would say very briefly what problems we identified on Ethereum. First off, Ethereum is clearly sharded nowadays. It scales horizontally for rollups. And another, I have a typo here. Another thing is unlocking the temporal dimension. Why should we care about it? So when you develop a contract on Ethereum nowadays, basically on any on-chain VM, whether it's EVM, Cairo, whatever, you're always limited, to thinking about now. You cannot really say, hey, what was my balance like 1 year ago? What caused the state transition? You can't really, smart contracts cannot really see the blockchains how humans see that. For a very good reason that I can talk about later in the questions. But now let me give you a better mental model behind it. At Herodotus, we really like to think of Ethereum as a book, but a book where you can basically see only a summary of this book. This is useful, but it's kind of limiting because you can basically see that for some reason Alice ended up in some state, but you cannot really see how we actually got there. You cannot see all the intermediate states. So that said, you cannot really see the blockchain as a human, and it's like again a book where you only see the summary. You cannot see all the transitions that happen in between and from what to what you transitioned. And storage proofs can exactly help you to unlock the potential of your applications and basically see more. So let me explain how it works and what is the workflow. So first, let's talk about the general technique, why why these things actually can be unlocked and made possible. So blockchains have a superpower. The superpower is basically the fact that the full history of the chain is committed to the latest block. How? Because there is a cryptographic linkage, because in the block header, we have a link to the previous block hash, which we call the parent hash. So if I prove that I know the preimage to this, I can decode the parent hash of the previous block and the previous block and the previous block and the previous block. So basically, as long as I have a valid block hash, I can access anything. But obviously, accessing that anything will require a lot of computational power and bandwidth. And that's how validity proofs can be very helpful. So let's talk about the structure of the block header and why you really need validity proofs in that case. So this is an Ethereum block header. It's a little bit outdated because I think there is no withdrawals hash and no base fee, but doesn't matter. So most important in our context, parent hash. If I'm doing some computation, I can prove that I know the preimage to this parent hash. And the preimage to this hash is, again, the same block header. So I can theoretically keep doing the procedure over and over again, and I can basically iterate through the entire blockchain. But as you can guess, doing that on-chain, it's a bad idea. Why? Because we have roughly, actually more than 80 million blocks on Ethereum so far. Each block header RLP encoded is more or less 1 kilobyte. Let's multiply 1 kilobyte times 80 million, you get 18 gigs. Imagine putting 18 gigs of data on a chain. That's going to end up very bad. Some people even made a test back in the days that putting a photo of a Lambo, which is a few megabytes, is more expensive than the Lambo. So we don't really don't want to do that. And that's how we can use validity proofs. And let me talk about it. So first off, we can execute this logic inside, for example, the Cairo VM. We can basically iterate the entire blockchain and prove the valid backwards transition from, for example, the block 1989, number 80 million to the genesis. And that's it, right? But are we going to do it every time we want to access a piece of historical data? Of course, no. It's very suboptimal. And for this reason, we would like to make this retrieval instead of n, we'd like to make it log n. And how can we do that? We can engage a one-time process, which is called the accumulation. And the accumulation is basically this idea that we can iterate through the entire chain, prove that this computation is correct, and at every step of this computation, at every iteration, we can just append some block hash to an MMR, Merkle Mountain Range. Really don't want to dive into Merkle Mountain Ranges today. Just to give you some mental model, you can think of it as a list of Merkle trees, basically. It's a brutal simplification, but let's stick to it. Yeah, and basically every time I iterate through the chain, I will just append a block hash to the Merkle Mountain Range. So the output of my final computation would be a root of Merkle Mountain Range, which probably contains only valid Ethereum block headers. And now disclaimer, we actually generate two types of Merkle Mountain Ranges at Herodotus. One built with Ketchak, so we can be EVM friendly, and one built with Poseidon, so we can use this inside circuits. So now coming back to the original part of my presentation, how can this actually solve historical data and reading state of layer 1 through rollups and rollups from other rollups? So we can verify this bunch of proofs that will generate this Merkle Mountain Range on layer 1, and then we can basically propagate it to other rollups. And very important part of the equation here is that rollups commit back to L1, right? So as long as we can access L1, we can verify the inclusion proof against the rollup state root, or we can prove that we know the preimage to a header, decode the state root, and then perform the entire computation. Of course, this comes with a delay, but it is still possible. So again, the same technique that I explained before can be applied also for accessing historical rollup data. I think this slide kind of summarizes that, but maybe let's dive more into the details. So the blockchain is 80 million blocks on Ethereum today. It's quite of a lot. Of course, we don't do it inside one ZK proof, inside one Stark. We actually generate a lot of Starks, and we just aggregate them on-chain. So basically, we verify one after the other in a predefined sequence and predefined order, and that way we can basically prove that, hey, if you take this proof, which iterates from the block 80 million to 80 million minus whatever size of the batch, this is the root of the MMR you're going to end up. Then we take another proof that transitions from X minus size of the batch. This is the next root of this one MMR, but keep in mind we generate two of them, and so on and so on. We can keep aggregating these proofs, and then the results can be just dispatched across multiple rollups so they can see that. And disclaimer, like I said, we generate two of them, one Ketchak, one Poseidon, so we can kind of use both. Okay, so I was talking about how we can actually access historical headers, as this is the most computationally intense part of the workflow. I hope you see that slide. If not, I'll do my best to explain. So what we achieved so far? So far, we achieved a way, and we build a protocol where we can basically pick up whatever block header without the need of like traversing the entire chain, because the MMR has been already generated. So I can pick just the block X, the header, then I can prove the preimage to this header, because again, the leaves of this accumulator are the hashes. So I need to provide the preimage to it. From that preimage, which is a valid block header, I decode the state root. Against the state root, I am able to verify a Merkle inclusion proof. So I can prove, for example, the existence of an account, supposedly USDC. And then against USDC, I take its storage root. What is the storage root? So on Ethereum and most stateful blockchains nowadays, we have the state is constructed in a way that it has two levels. The first level is the tree of accounts, and the second one is that each account has a tree of storage slots. So again, we prove first an existence of an account, then from that account we retrieve the root of its internal tree, and against that tree we prove a value of a specific storage slot. So now, just to sum it up, we have three steps. First, from the MMR, take the block header. Against the block header, the state root of the block header, verify an account proof. Against the account storage hash, verify a proof for the storage slot. And of course, this can be costly, but still, the most costly part is actually traversing from the entire chain. And here, this entire workflow can be executed either directly on-chain. We can perform this verification inside the smart contract, or we can engage some snarks or starks, depending on how data intense our use case is. So I mentioned use cases. Let's talk about them. So first one, insurance. We can access historical data. So I can say, hey, listen, if you prove me that this specific account suddenly will end up at having 0 ETH for whatever reason, then trigger a payout. And of course, you don't want to, have like a listener that if this condition is met at this very specific point in time, then you trigger something. Like, it's very hard to achieve that, right? You ideally want to be able to see something in the past. So even if the actual action is met, the actual condition is met at block X, you can still trigger the payout at X plus 10, thanks to the ability of seeing the past. And you can even do it on layer 2s. You can access data that normally is not accessible to smart contracts. For example, a volume-weighted average price. It's not doable at all. You need to engage an oracle. Provable airdrops. How airdrops work today? Usually it's just a team SQL query on Dune. You generate a CSV, you Merkleize the CSV, and you just put it on the chain, and then you expose like a server that allows you to fetch a Merkle inclusion proof against that root. So it's highly trusted. What if you can just prove that, hey, I actually meet the criteria? So I interacted this amount of times with Uniswap, I interacted this amount of times with whatever protocol, and so on and so on. Next use case, access to rundown. So for those of you who don't know, now it's possible to actually access some randomness on-chain, and this randomness is in the block header of the execution layer under the mix hash. And again, if we can access historical block headers, you can also access historical rundown. So for example, what we can do, we can say, okay, we build some application that says, if at this specific block the randomness is this and this, then perform a specific action. So finally, we can use randomness in a nice manner. Another use case, account recovery. If you have the ability to look in the past or into the state of another chain, you can say, hey, if this account is not being used for more than 6 months, that it probably means that you want to add, I don't know, like a second signer or something like that. technical problems. It's back? Okay, cool. So now just to conclude my presentation, I will leave some time for questions. Thanks to validity proofs and all these techniques that I mentioned around storage proofs, you can basically supercharge on-chain VMs. Why? Because finally we have VMs that don't only have access to the summary, but they have access to every state transition, because you can take a look at logs, you can take a look at receipts, and also you can look at these intermediate summaries throughout the whole history of the chain. And this not only applies to layer 1, but you can also do it for rollups. So effectively, thanks to storage proofs, we can finally, smart contracts can look at Ethereum as, just a database. And that's this. I think that's about my presentation, and happy to answer any question.